In late 2024, a training run completed in China that the public announcements described in aggregate terms 50,000 chips, 1.6 trillion parameters, a frontier-class model called LongCat, without ever naming the accelerator that bore the load. That chip is on the table now. The announcements were careful in exactly the way that careful omissions are informative. The headline numbers were offered, and the component beneath them was not. That gap is the first thing to notice, because a gap in a public disclosure about hardware at this scale is not accidental. It is a decision, and decisions of that kind point toward the layer the speaker does not want followed. The deepest layer of this machine is not what the headline count suggests. 50,000 chips running a 1.6 trillion parameter model is a system-level fact. The component-level fact is different. The sovereignty that the announcement implies is assembled rather than wholly manufactured at home, and the shape of what is assembled reflects in every subsystem the restriction environment in which the chip was designed. The constraint that was intended to prevent this machine is legible in its architecture, not as an absence, but as a presence. In the proportions of the die, in the sourcing of the memory stack, in the maturity of the software layer that translates hardware capability into actual computation. The cuts run from the compute die outward to the cluster announcement, and then inward through fabrication, memory, interconnect, software, and supply chain to the buried constraint that determined the machine's proportions. Each pass exposes a different layer of what it meant to build a chip, when the leading alternative was structurally unavailable. We begin at the outer shell, with what the cluster announcement does and does not say. The LongCat training run, as reported by the organizations involved and covered by Chinese state and industry media in late 2024, involved a cluster of roughly 50,000 accelerators and produced a model with approximately 1.6 trillion parameters. These figures are the organization's own claims. No independent third party has audited the cluster configuration or verified the model's achieved performance against a published benchmark. The scale is notable on its own terms. Very few organizations anywhere have operated training clusters of this size, and the parameter count places LongCat in the range that the research community describes as frontier class. What the announcement omits is the accelerator supplier. That omission is not an oversight in a disclosure of this visibility. Chinese technology announcements at this scale have become deliberate about which components are highlighted, partly because component-level specificity invites scrutiny of exactly the supply chain questions this dissection is going to trace. The headline is shaped by the questions its authors preferred not to answer publicly, and that shaping is the outer layer. The first cut reaches the compute die, and the question it opens is whose architecture and whose fabrication process produced it. 3 domestic accelerator lineages are plausible candidates for a cluster of 50,000 chips. Cambricon's MLU series has been deployed in data center configurations, and the company has disclosed cluster-level interconnect work, but its publicly documented largest deployments are considerably smaller than the scale reported for LongCat. MetaX is a newer entrant founded in 2019, fabless with an architecture adjacent to the graphics processor lineage, and while it has disclosed data center parts, no public record establishes a deployment at anything approaching this scale. Huawei's Ascend 910 series, and its successors, is the candidate most consistent with the scale of the LongCat run. Huawei has publicly described Ascend-based clusters in the thousands of chip range, and Chinese cloud providers have disclosed Ascend procurement at volumes that would be consistent with a 50,000 chip aggregation across multiple customers and installations. This identification is inference from disclosed procurement and cluster architecture patterns, not from a confirmed independent teardown. The analysis proceeds with Ascend as the most probable specimen, with that caveat held explicitly through every subsequent layer. The Ascend architecture uses a tile-based design organized around what Huawei describes as a Da Vinci core, a tensor computation unit optimized for matrix operations. The architecture is not compatible with Nvidia's CUDA programming model, which means the software ecosystem accumulated around CUDA over roughly 2 decades does not transfer. That incompatibility is a cost that every organization deploying Ascend hardware has paid in engineering time. It also reflects a design decision made when the probability of CUDA access was already low. The architecture carries its origin conditions in its structure. An architecture shaped by the expectation of isolation is different in its priorities from one designed to compete within an existing ecosystem, and the Ascend tile design's emphasis on deterministic memory access patterns over programmability breadth is exactly that kind of priority shift. The chip was designed to work without the ecosystem it could not have. The second cut reaches the fabrication node, which is where the export restriction becomes physically measurable. Huawei's own disclosures and analyst estimates place the Ascend 9 10B and its successors at a process comparable to a 7-nanometer generation manufactured at SMIC, China's leading domestic foundry. SMIC reached a 7-nanometer-class process through immersion lithography, rather than the extreme ultraviolet lithography that TSMC and Samsung use at this node. This distinction matters for yield and for the physical size of the die. Extreme ultraviolet lithography exposes each circuit layer with shorter wavelength light, allowing finer feature resolution with fewer exposures. Immersion-based approaches at the same nominal node require additional mask layers to achieve comparable resolution, which increases the number of process steps, extends cycle time, and produces lower yields than an extreme ultraviolet-enabled equivalent. Independent analysts have noted this yield gap, though exact figures are not publicly confirmed for SMIC's specific process. Nvidia's current data center accelerators are manufactured at TSMC on processes several generations ahead of SMIC's current demonstrated capability. The node gap has a physical consequence that compounds across a 50,000 chip cluster. The same transistor count on an immersion-based process requires more silicon area than on an extreme ultraviolet process at a comparable node. That additional area must be cooled, powered, and packaged. Across 50,000 chips, the area premium translates into a thermal and power management problem that scales with every rack in the cluster. Consider what it means to fill the same functional floor plan with components that each occupy a larger footprint. The transistors perform the same operations, but the infrastructure required to keep them within their operating temperature range grows with the footprint, not with the transistor count. The node gap is that difference, repeated 50,000 times across a building full of servers. The restriction did not prevent the chip. It determined the chip's proportions, its power draw per rack, and the cooling infrastructure the cluster requires. The third cut reaches the memory stack, and this is the layer where the supply chain uncertainty is sharpest. High bandwidth memory, the stacked dynamic random access memory bonded to or packaged beside the compute die and accelerators of this class, is produced at manufacturing scale by a small number of companies. SK, Hynix, Samsung, and Micron are the principal suppliers. Chinese domestic dynamic random access memory production has reached DDR5 class products at companies including Chongshin Memory Technologies. But high bandwidth memory production requires advanced through silicon via stacking processes that Chinese domestic producers have not publicly demonstrated at production scale as of mid-2025. Through silicon via stacking involves drilling vertical channels through individual memory dies and filling them with conductive material to create direct electrical connections between stacked layers. The process requires precise lithography alignment across multiple layers and a yield discipline that takes years to develop. Chongshin Memory Technologies has announced high-bandwidth memory development programs, and Huawei has publicly discussed plans to integrate domestic memory, but no independent source confirms domestic high-bandwidth memory and volume production at the specifications required for a cluster of this scale. Earlier generation teardown analyses of Ascend hardware identified SK Hynix high-bandwidth memory in some configurations. Whether this remained true in the configurations that powered the LongCat run is not publicly confirmed. The memory stack is the layer where the sovereignty of the training run is most uncertain and most consequential. Memory bandwidth is not a secondary specification for large-scale training. The ratio of compute throughput to memory bandwidth determines how effectively the compute die can be kept busy during a training step. A chip whose compute units are faster than its memory can supply data while stall, waiting, and those stalls scale with model size. At 1.6-trillion parameters, the working set of waits and activations that must move between memory and compute during each training step is enormous. If the memory stack in the LongCat cluster carries foreign-sourced components, the run's independence is conditional on supply chains that export control policy could, under different conditions, have severed. The uncertainty is not resolved by the announcement, and the announcement does not address it. The fourth cut reaches the interconnect fabric, the layer that determines whether 50,000 chips function as a single machine or as 50,000 separate accelerators that happen to occupy the same building. A training cluster of this scale requires two distinct communication layers. The intranode interconnect links chips within a single server, and Huawei has disclosed a proprietary high-speed chip-to-chip interface used in its Atlas server line for this purpose. The internode fabric links servers across the cluster, and this is where the component picture becomes more complex. Optical transceivers carry traffic between nodes, and for data center interconnect, domestic Chinese manufacturers have developed credible products, giving this part of the layer a more established domestic sourcing story. The switching silicon that routes traffic between servers, however, has historically drawn on products from Nvidia's Mellanox and InfiniBand line, or from Broadcom's Ethernet switching portfolio in Chinese data center deployments. Domestic switching silicon from Huawei and other Chinese vendors has been deployed in some configurations, but whether the LongCat cluster's internode switching is fully domestic is not publicly confirmed. The interconnect's significance at 50,000 chips is structural. A training step in a large-scale run involves distributing input data to accelerators, computing partial results on each, communicating those partial results across the cluster to aggregate them, and updating the model weights before the next step begins. The time spent in communication is not compute time, and a cluster that spends a large fraction of each training step waiting for the interconnect to complete its work is not operating at its headline chip count's worth of compute. The actual effective throughput of the cluster depends on how efficiently the interconnect architecture handles the synchronization problem, and that depends on the latency and bandwidth of every link in the fabric. The announced parameter count describes what was trained. The interconnect architecture determines how much of the cluster's theoretical capacity was available to train it. The fifth cut reaches the software stack, the layer the specifications do not list, and the layer most resistant to closing through procurement. Huawei has developed a software ecosystem called CANN, which provides the operator libraries, compiler backends, and runtime management tools that allow training frameworks to address the Ascend hardware. PyTorch and PaddlePaddle have published Ascend backend support, and the frameworks can be made to run on Ascend hardware. The maturity and coverage of this support relative to the CUDA ecosystem is an open question that public benchmarks have not settled. The CUDA ecosystem's depth is not primarily a function of its design. It is a function of time, of the accumulated optimization work of researchers and engineers who have spent years finding efficient ways to express training algorithms on Nvidia hardware. Kernel implementations refined over thousands of training runs, numerical recipes for stable large-scale training, memory management strategies that avoid fragmentation at the scale of trillion-parameter models. None of this transfers automatically to a new architecture. Some of it must be rediscovered, and some of it requires redesign from a different starting point. The LongCat runs compute utilization rate, the fraction of the cluster's theoretical peak throughput that was actually available for computation during training steps, is not publicly reported. The company's own claim is that the run succeeded and that the model exists. The efficiency ratio, the number that would allow a meaningful comparison against what the same parameter count would require on a leading-edge alternative cluster, is a number the announcement does not provide. An immature software layer can leave a substantial fraction of a chip's transistors idle during a training step, and the absence of a reported utilization figure is not conclusive in either direction. What it is informative. The deepest software layer is where the gap between theoretical capability and operational performance lives, and that gap is the one the announcement is least equipped to address. The sixth cut maps the supply chain by sourcing geography, layer by layer, and produces the picture the headline cannot. The compute die's design is domestic in origin, Huawei's own architecture team, and its fabrication is at SMIC, a Chinese domestic foundry. The silicon itself is the most credibly sovereign layer of the machine. The package substrate and advanced packaging processes required to bond the compute die to its memory involve equipment and material supply chains that include foreign inputs, though domestic packaging capability has improved materially in recent years. The memory stack carries significant uncertainty. As noted, whether the high bandwidth memory is domestically sourced is unconfirmed, and the domestic production capability for this component at the required specifications is not yet established. The interconnect switching, if it includes foreign origin silicon, represents a dependency at the cluster's communication backbone. The software stack is domestically developed but carries a maturity gap that is measured in engineering years, not in procurement cycles. The power delivery and cooling infrastructure in a cluster of this scale are areas where domestic supply chains are relatively well established and represent a genuine strength of the domestic industrial base. The supply chain map is not a verdict on the run. It is a description of where the industrial base is strong, where it is developing, and where it remains conditional. Each layer's sourcing geography is a measure of how durable the capability would be under sustained pressure on the foreign components it still requires. Strip the cluster to its densest fact, and this is what the layers expose. The export control regime that was designed to prevent China from training frontier models at this scale did not prevent the training run. It determined the architecture of the chip that ran it. The Ascend die is larger than it would be under a different lithography regime, and that additional area is present in every chip across all 50,000. The memory stack carries a dependency the domestic industrial base cannot yet fully replace, and that dependency sits at the layer most critical to the ratio of compute to weighting. The software ecosystem is younger than the problem it is being asked to solve, and the efficiency figures that would measure the gap between theoretical and actual performance are not published. The interconnect fabric has layers whose sovereignty is conditional on foreign switching silicon. Each of these conditions is a direct consequence of the restriction environment in which the machine was designed and built. The constraint is not absent from the machine. It is present in every layer, shaping proportions, forcing substitutions, and leaving the utilization number unreported because the utilization number is where the constraint's cost is most visible. Three things this dissection cannot settle, stated plainly. The accelerator identification, the memory sourcing, and the interconnect configuration all rest on disclosed procurement patterns, analyst estimates, and earlier generation teardown analyses. No independent party has opened a LongCat cluster accelerator and mapped its components against their sourcing geography. Every specific inference in this dissection carries that uncertainty, and the organizations involved have not provided component-level disclosure that would resolve it. The training run's compute utilization rate is not publicly reported, which means the efficiency comparison against a leading-edge alternative cluster cannot be made with the available evidence. The achievement is real. Its efficiency relative to alternatives is genuinely unknown. The high-bandwidth memory production gap, the extreme ultraviolet equipment restriction, and the software ecosystem maturity gap are not problems that resolve through procurement or through announcement. They are development cycle problems measured in years, and they are not closing at the same rate as each other. What the dissection can settle is the structure of the achievement, the system-level milestone is genuine, the component-level sovereignty is uneven, and the shape of the unevenness reflects the restriction environment directly. The LongCat training run, read layer by layer, is an account of what an industrial base can assemble when it is motivated by the certainty that the alternative is unavailable. The compute die is domestic in design and fabrication. The memory stack is uncertain. The interconnect carries conditional dependencies. The software layer is younger than the problem. The efficiency figures are unpublished. Taken together, the layers describe a machine that was built under constraint and that carries the shape of that constraint in every layer, not as a failure, but as a record of what the restriction actually accomplished, which was not prevention but transformation. The chip that ran a 1.6-trillion-parameter model without Nvidia is also the physical evidence of what it took to do so. The restriction that was meant to stop this machine is the reason its inner layers look the way they do. What the teardown reports logged as specifications, the layers read as biography. The next object worth opening is the one behind the memory gap, the high-bandwidth memory development program at Changshan Memory Technologies, and what its package geometry and process approach reveal about how close domestic production is to closing the stack. If you want that one on the table next, put it in the comments, subscribe if you want to be in the room when the next one is opened.